Well, you're just drawing each individual, and this gets into a parallel circuit because those things are hooked in parallel. But the more branches you have in parallel, the more current each branch has, and it just adds up, right? So when we get to parallel, you'll see why this is, right? Okay, but notice that the 15 plus 6 plus 3 adds up to 24. And this is one of Kirchhoff's laws, by the way, that the voltage drops in the circuit add up to all the voltage gains. If you do an entire loop, you end up back at 0, right? So if I start here, and I go around, I go up 24, down 3, down 6, down 15, I'm back to 0. Yeah? Okay? So there we have it, right? So that's how you do it. Whenever it's a series circuit, you know, don't ever go, gee, should I solve it? Just solve it. You know, it's like Nike, right? We're just going to solve it. And that's how we do it. Yeah, just do it. Now, here's the weird thing, and kids always have a hard time thinking about this. So here's an analogy I think that's going to help you think about it. What they'll want to do is they'll want to say, oh, well, the current starts out really big. And after it goes through the first resistor, the current gets less, and then it gets even less or something like that. Or they'll go, how does this resistor change the current here? That's sort of weird, isn't it? If you were watching this current here, and I had a variable resistor here, a potentiometer like this thing. This is a variable resistor. And I was sitting there sliding this and making it go through more of the nichrome wire or less of the nichrome wire. You would see the current here getting less and more and less and more, even though it hasn't at this point encountered this resistor yet. Isn't that weird? Okay, but here's an analogy that I think will help. Think about current as ping pong balls being pushed through a tube. Yeah? Okay? You're pushing them in one end, they're coming out the other end. And if you push one in, one comes out the other end. If you push 2 in per second, 2 come out the other end every second, yeah? This is like a series circuit, isn't it? If I'm pushing 3, in this case, 3 ping pong balls per second in one end, 3 come out the other end. At any point in this thing, 3 are going by you every second, correct? Yeah? Now, this tube is flexible. It's a flexible plastic tube, and if you grab the tube and sort of press on it, it makes it hard for the ping pong balls to slide through. Are you picturing that? Yeah? And if 2 or 3 of you hold on to it with differing amounts, the amount of resistance is just the sum of the resistance, isn't it? And each one of you is making it harder as you grab it, right? If you grab it any amount, you're making it harder to push ping pong balls through the tube, correct? And if the current's going this way and you grab the tube even on that end, it's going to slow the rate on this end too, isn't it? Because they're all together, right? And that's the same way with electrons going down the wire. They can't pool up and bunch together because to do that would require tremendous voltages, right? Okay, not more than like 12 volts, like tens of thousands, hundreds of thousands of volts to pool up a coulomb of charge, right? With our Van de Graaff, we had, what was it, 10,000 volts or something like that, right? And we had like a microcoulomb of charge on there, right? Okay, so that's how a resistor that's later on in the circuit can affect the current earlier on. Does that help? Does that analogy help? Yeah. So, and I would love to take credit for it, but some student came up with this analogy, and I've forgotten who it was. It's sad, but there it is, right? Okay, so let's do this one. Whiteboard time.